Well, okay, so let's talk about something very important. So I want to talk about a foundational idea in quantum mechanics that's called wave function collapse. Perhaps you've heard of this before. But, well, again, let's go back to basics. What's the modern statistical interpretation of the wave function? It's a thing that gives you the probability distribution of where you would find a particle if you perform the measurement. It also gives other things, as you could see. We can tease out from it things like average momentum, standard deviation of momentum. So it knows a lot about a lot more than the position. But at face value, this equals probability distribution of position measurement outcomes. Okay? It's important to understand when we talk about probability, we have in mind a frequentist perspective. That is, we imagine an ensemble of systems, like replicas of the systems, identically prepared, and then we start measuring away, right? So I have, say, a harmonic oscillator, a harmonic oscillator, harmonic oscillator, harmonic oscillator, harmonic oscillator, right? So n harmonic oscillators. I prepare them all in a particular state at t equals 0. For example, psi 1, right? Okay, so at t equals 0, all of these are prepared in some way. Do they have to be prepared in one of the modes of the harmonic oscillators? No. So let's say I prepare them all to be in some initial wave function, right? So some identical initial wave function. Okay. So here I'm just gonna, okay. That's what I'm doing here. So what happens after is that the wave function evolves in accordance to the Schrödinger's equation. Okay, so this is, I know the wave function is complex. I'm just symbolically drawing the wave function. Okay. So this is called preparation. After that prep, the wave function evolves in accordance to Schrödinger's equation. Okay, the full Schrödinger's equation. So then at time t, I perform a measurement. So at time t, the wave function will be, at time t, I'm thinking what's the best thing to say first to you. At time t, after the prep, okay, I do. At time t after the prep, I perform a measurement of some quantity t. At that time, the wave function has evolved from its initial form. It is now some function of space and time, right? So let's say at time t naught, okay, just to be concrete, t naught, a specific time. Wave function over space at time t naught, right? At t naught. And then let's say that now it takes on some other form, right? So this is, okay, so again, how many? 5. So here's my 5 replicas of my harmonic oscillator. So here are 5 replicas of my harmonic oscillator. And now let's say it looks like this. It has evolved. It's not the same as what it was to begin with. The wave function evolves under the action of the Schrodinger's equation, okay? Schrodinger's equation tells the wave function how to evolve. I mean, no one tells the wave function, but that's how we describe, that's how we predict the evolution of the wave function. Okay, so again, this parabolas, these are potential energies, right? I hope you understand that. So what I'm trying to say is I have replicas, in this case, replicas of harmonic oscillators. I'm just drawing 5 of them. I prepare all of them in some initial state. That state evolves, that wave function evolves. And at sometime t naught after the preparation, for example, 10 minutes after the preparation, I'm going to perform a position measurement. Right before I perform the position measurement, the wave function will be this, okay? So this is at that time, and right before the measurement. Okay, so at time t naught, I am going to perform a measurement of some quantity: position, momentum, charge, mass, angular momentum, some physical quantity. At that time, meaning right before I perform the measurement, the wave function has matured, it has evolved from its initial form, and it is now this, right? So this is, again, it is now this. So this is the wave function right before I make the measurement. So between preparation and the measurement, the wave function evolves in accordance to the Schrodinger's equation. So that's the quantum dynamics. In classical mechanics, we have a different way of describing a state of a particle. We describe it by its position and momentum. And again, between the preparation and some time t, position and momentum evolves according to the Newton's equations, okay? In quantum mechanics, we don't deal with position momentum. We can measure position and momentum, but that's not what describes the state of the particle. The wave function describes the state of the particle. It contains the whole information. And in quantum mechanics, it evolves in accordance to the Schrodinger's equation, okay? I hope this is clear. okay? All right, so, and now here's the brouhaha question. What happens to the wave function after, let's say right after the measurement? I.e., what does a measurement do to the wave function? I want to make it clear, measurement does not necessarily mean that there's a conscious human being, okay? Measurement is a form of interaction. So in between the prep and the measurement, the particle was interacting with something else by means of a potential energy function. So for example, if it's an electron interacting with a proton by means of a potential energy, the electron-proton potential energy. In this example that I'm drawing, it's some kind of a harmonic oscillator that's interacting with something else by means of a harmonic oscillator potential energy, right? You can think of this as a mass on a spring interacting with a wall, but it doesn't have to be that. I mentioned yesterday that if you have two masses, that's kind of equivalent to a mass on a spring interacting with a wall. So you have some kind of interaction, and the wave function evolves during that interaction. And then at some point you perform a measurement. Measurement is another type of interaction. It's a different type of interaction. But a measurement is a form of interaction, okay? And it's not abstract, right? So for example, if I want to measure, if I have a double slit experiment and I want to measure the position of the electron interacts with the film at the screen of the double slit apparatus. It materializes into a point. Send another electron, it materializes into another point. So there's a physical physical interaction of the electron with the chemistry of that film, and it's an interaction like any other, okay? So this is the question. Let's look at an example. For example, I will measure a position. So here's this wave function that I drew. Let me try to reproduce its shape, right? So here's the wave function. So here's space. Here's the wave function over space at that moment t naught. Well, first, where am I going to find the particle? Well, sometimes I will find here, sometimes I will find here, sometimes I will find here. Okay, very rarely I will find it here. And the probability distribution of where I will find it is given by psi star psi. This is probability distribution x, psi star psi. And it will also look like some kind of a peaky thing, right? So something like that, right? So this is, I'm most likely to find a particle, for example, harmonic oscillator, mass on a spring. Here, less likely in the wings. So I have an ensemble of these harmonic oscillators. I perform a position measurement on the first guy. So here's system number one. I perform a position measurement, and I found that the particle is here. I go to system number two. I say, you measure your position. I perform a measurement, and boom, I find the system here. System 3, okay, you're next. I'm going to perform the position measurement. For example, like a film in a double slit experiment. Boom, I find it here. And so on. Fourth, here. Fifth, here. And I will end up with a histogram of particles, and that histogram will be given by this probability distribution. Okay, so most of the particles will be found here, sometimes here, sometimes here, sometimes here, but a lot of them will be found here. And so if I accumulate those particles, that histogram will match that probability distribution. That's what we mean by probability distribution. It's larger where the particles are found the most frequently. And okay, so in system 1, I now found that the particle is here. In system 2, I now found that the particle is here. In system 3, I found that the particle is here. So let me reproduce that drawing. So here's system 1. Here is the wave function right before the measurement. And I found the particle right here. So this is right before the measurement. I found the particle here when I performed the position measurement. And the question is, what is the wave function right after that? Pause the video and think about it. Okay, so situation, and I keep drawing the parabola to remind you that we're dealing with a harmonic oscillator. In the background, it's a harmonic oscillator interaction. It's a linear restoring force, mass on a spring, or something else that acts like a harmonic oscillator. Situation right after the measurement. What is the wave function right after the measurement? Think about it. This is the crux of the matter. Now, we found the particle right here. The particle is right here. That means right after the measurement, I know that the particle is definitely here. It's not here, and 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 it's not here. What's the probability density of a particle here? 0. Here, 0. Here, 0. Here, 0. Here, 0. Here, 0. What's the wave function there? It's kind of like the square root of the probability. Not exactly a square root, because it's a probability density is psi star psi, not just psi squared. But basic, it's like a square root kind of thing. Well, if the probability here is 0, then the wave function here is 0. So the wave function is going to be 0 everywhere. Let me use a different color, right? So let me use a color orange. I want to use a color orange so we distinguish the wave function right before the measurement and right after the measurement. Okay. So the particle is not here, not here, not here, not here, not here, not here, not here. And so that means the wave function is 0 there. Because the probability density at that point is basically wave function psi times wave function star times the wave function. And remember, the area under the wave function, under the probability density, sorry, must always be 1 because the particle has to be somewhere. And now we know where it is. So the wave function is going to be this kind of a peak, a very narrow peak. If you really could measure the particle's position to infinitesimal precision, it would be infinitesimally thin and infinitely tall peak with an area 1 under it. Mathematically, this is called Dirac delta function. Maybe you know that. If you don't, it's okay. We can never perform a position measurement to arbitrary accuracy So it will have a finite width, but a very small width, and the width will be given by the accuracy of the measurement. Perhaps maybe it would be something like this, or maybe it will be a very narrow Gaussian, or maybe it would be kind of a triangle. But the point is, the support of that wave function after the measurement will be equal to the width, will be equal to the precision of your position measure. We usually don't fuss about it when we say that it has collapsed into an infinitesimally thin peak. Mathematically, it's called Dirac delta function. If you know it, great. If you don't, relax. So look, this is right before the measurement. This is situation right after the measurement. Let me use the so in that instant when you've performed the measurement, the wave function collapsed. This is called wave function collapse. Not collapse, collapse. Okay, it went from being this to being this upon a measurement. Okay, and what collapsed the wave function is measurement. In this case, it was a measurement of position. When I measured the position, the particle took a stance. It took on a particular position. Before the measurement of position, where was the particle? The particle's position before the measurement is undefined. When I was grading a video quiz 5, some students wrote something like, the particle's position will be found. I don't remember exactly the language, but from what I could gather from your answers, is that it seemed that you think that the particle's position is well defined, we just don't know it. The particle's position before the position measurement is a nonsense. It doesn't exist. That's the wonders of quantum mechanics for you. The act of measurement forces the particle to take a stance and to take on one of the possible values of position, weighted in accordance to the position probability distribution. That's the modern interpretation of quantum mechanics. I didn't develop this interpretation. I didn't invent it. I'm just simply communicating to you the sort of the best standard understanding of quantum measurements. Now, there are alternative interpretations of quantum mechanics. We're dealing with a standard interpretation called Copenhagen interpretation. I tried to be as clear as I could in concerning the position measure. What if I measured something else? The wave function is in this purple state, and now I want to measure not its position, but its momentum. Think about it. I'm going to discuss that in a separate video. Thank you.